Picture this. It is a Tuesday afternoon and you are spinning up a new microservice. You run the command you have typed 1,000 times npm install. The terminal scrolls and everything looks green. But behind the scenes, a nested dependency just executed a hidden post install script. This script scanned your environment, found your env file containing AWS secret keys, and silently exfiltrated them to a remote server. By the time your local server is up, your production environment is already compromised. This isn't a hypothetical scenario, it is a daily reality in the modern ecosystem. We often think of dependencies as static code, but they are active agents with your full user permissions. In this lecture, we will strip away the illusion of safety provided by simple lock files and build a real defense-in-depth strategy for 2026. I will show you exactly why a simple lock file is useless against these dynamic, script-based execution attacks. The old way of working was based on implicit trust. If a package was on npm, we assumed it was safe. But as a senior engineer, I can tell you that trust is now our greatest vulnerability. We are shifting toward a zero-trust model for dependencies. This involves two major frameworks you must master: Sigstore and SLSA. Sigstore provides the tools to sign and verify code without the headache of managing PGP keys, while SLSA supply chain levels for software artifacts gives us a checklist to ensure the integrity of the build process. When we talk about provenance in 2026, we are talking about a cryptographic proof that the code you are running is exactly what the author wrote, built on a secure CI/CD pipeline. This is how we move from hoping a package is safe to verifying its entire lifecycle. But this shift requires a complete change in how your CI/CD pipeline treats external code. However, before we fix the pipeline, we must understand the sheer scale of the threat we are facing today. Why are we talking about this so urgently in 2026? Because the scale of attacks has exploded. We are seeing over 450,000 malicious packages identified annually on public registries. Attackers are no longer lone hackers. They are using sophisticated automation to flood npm with malware within seconds of a popular package being updated. They use LLMs to generate realistic-looking readmes and documentation to fool even experienced eyes. Most of this malware targets the PMP ecosystem specifically because of its deeply nested dependency trees. When you install one top-level framework, you might be pulling in 1,000 sub-dependencies. This dependency hell has become an attack surface. If just one tiny utility package at the bottom of the tree is compromised, your entire application is at risk. It's a numbers game, and the attackers are winning because they only need to find one weak link. But wait, it gets worse when we look at how these packages actually sneak into your specific environment. But in the past, we mostly worried about typo-squatting someone registering React DOM with tombs. That was easy to spot if you were careful. But today, we face dependency confusion. This is far more dangerous because it targets your internal, private packages. If your company uses a private package named itcorp auth, an attacker can publish a public package with the exact same name, but higher version number, like 99.9.9. By default, many package managers will prioritize the higher version from the public registry, pulling the attacker's code directly into your production build. This bypasses your internal registry entirely. This is why tools like SBOM's software bill of materials are becoming mandatory. An SBOM is like an ingredient list for your software. It tells you exactly what is inside, where it came from, and who signed it. Without an SBOM and proper registry scoping, you are flying blind in a storm. This chaos is exactly why the next chapter on the anatomy of a modern attack is non-negotiable for any lead engineer. In many development teams, there is a dangerous sense of security surrounding package lock.json. We often treat the integrity hash as a seal of safety, believing that if the hash matches, the code is secure. This is a fundamental misunderstanding of what a lock file actually does. In the field, I see teams religiously committing lock files to ensure deterministic builds, which is great for consistency, but it does absolutely nothing to verify the intent of the code. If an attacker gains access to a popular package and publishes a malicious version 1.2.3, and you run a standard update command, your lock file will faithfully record the SHA-512 hash of that malware. From that point on, every developer on your team and every CI/CD runner will consistently install the exact same poison. The lock file is a consistency tool, not a security tool. It ensures you get the same bytes every time, but it cannot tell you if those bytes were written by a friend or a foe. This is the first gap in the supply chain that we must acknowledge. But wait, if the lock file isn't the problem, is it the person behind the code? Let's look at how even the most trusted maintainers become accidental villains. So how does the poison get into the registry in the first place? The most common method in modern attacks isn't a complex zero-day exploit. It's a simple account takeover, or ATO. Most maintainers of popular NPM packages are individuals working in their spare time, often without multi-factor authentication enabled on their registry accounts. Attackers use credential stuffing, phishing, or even social engineering to hijack these accounts. Once they have access, they publish a new version of a trusted package. To the outside world, this looks like a legitimate release from a trusted developer. It might even include a valid PGP signature if the attacker stole the private key from the maintainer's local environment. In the real world, I've seen official packages that have been clean for 10 years suddenly start exfiltrating environment variables. because a single developer's laptop was compromised. This bypasses all traditional trust models because the source itself is now the enemy. This leads to a terrifying reality. The official registry is now the primary distribution channel for malware. But how do they hide this malicious code from our eyes? This is where the technical trickery begins. Modern malware is rarely obvious. You won't find a file named stealer.js in the root directory. Instead, attackers use deep obfuscation and dynamic code execution to hide their tracks. They might use buffer from with base64 encoded strings that decode into executable scripts at runtime, or they might hide the logic inside a minified file that looks like a legitimate build artifact. Even more clever is when they place the malware deep within a dependency of a dependency of a dependency. In a standard project, you might have 1,000 transitive dependencies. When you run a security audit, you're usually only looking at the surface. Below that surface, a single line of code in an obscure utility library can be triggered only when a specific environment variable like node env dual production is present. This targeted execution makes it nearly impossible to detect during local development. I have seen cases where the malware remained dormant for weeks, waiting for the right conditions to strike. This brings us to a critical realization. Our current tools are looking for known vulnerabilities, but they are blind to intentional, obfuscated malice. Now, let's look at the most common door these attackers use to enter your system, the installation script. When you run pmem install, you are effectively giving every package in your tree permission to run arbitrary code on your machine through lifecycle scripts. Scripts like pre-install, post-install, and install are intended for legitimate tasks like compiling native binaries, but they are the #1 vector for initial access in supply chain attacks. Because these scripts run with the same privileges as the user who ran the install command, they can access your SH keys, modify your shell configuration, or even install a persistent rootkit. In professional environments, developers often ignore the ignore scripts flag because many essential packages rely on these scripts to function properly. This creates a massive blind spot. We've been trained to trust the process, but in the field, I tell my teams, treat pm install as curl py-pushe. Every time you add a package, you are trusting it not just to provide a function, but to safely execute code during your build process. This is the pre-runtime attack surface. But it doesn't stop at the build phase. It follows you into production. What happens when a build time script successfully executes? It doesn't just steal a file and disappear. Modern attackers use these scripts to turn your production environment into a persistent backdoor. For example, a post-install script can detect it's running in a CI/CD environment like GitHub Actions or Jenkins. It then injects a tiny snippet of code into the project's source files or its build pipeline. This injected code might open a reverse shell or start a hidden background process that communicates with a command and control server. By the time your application is containerized and deployed to the cloud, the malware is already baked in. It becomes a living off-the-land attack where the malicious code uses your own legitimate infrastructure to hide. From my experience, debugging these is a nightmare because the source code in your repository looks clean, but the artifact that actually runs is compromised. This is why verifying the integrity of the build process itself is just as important as verifying the code. But wait, how much code are we actually talking about? Let's visualize the scale of the problem. In a modern React or Nest.js project, you might only add 10 direct dependencies to your package.json, but after running install, you'll find over 1,000 packages in your node modules. This is the transitive C. Your security is only as strong as the weakest, most obscure dependency in that massive tree. Attackers know this. They don't target React itself. They target a small library that React's build tools happen to use. This creates a massive attack surface that no human can manually review. In the field, we call this transitive risk. One small update to a package you didn't even know you were using can bring down your entire security architecture. Most developers focus on the tip of the iceberg code they wrote, while the 90% below the surface is a complete black box. We need a way to verify the entire chain of custody from the original author to the final production server. We've mapped out the minefield, but how do we actually clear it? In the next chapter, we're bringing in the heavy artillery, the Sigstore defense stack, designed to rebuild the chain of trust from the ground up. In my years in the field, I've seen countless security initiatives fail for one reason: friction. For decades, we tried to secure software with PGP keys. Let's be honest, key management is a nightmare. Developers lose keys, forget passwords, or worse, hardcode private keys into CI scripts. Sigstore changes this narrative. Its mission is to make code signing as ubiquitous and invisible as HTTPS became for the web. Instead of managing long-lived private keys that can be stolen or lost, Sigstore uses short-lived certificates based on your existing identity, like GitHub or Google via OADC. It provides a standard for signing, verifying, and checking the integrity of artifacts without the administrative overhead that usually kills secure adoption in fast-moving dev teams. This is the foundation of a modern software supply chain. But you might be wondering, if there are no permanent keys, how do we actually prove who signed the code? This brings us to the core engine of the system, fulcio. Fulcio is the certificate authority of the Sigstore stack, and it solves the stolen key problem by issuing certificates that only last for about 10 minutes. Here is the workflow. When a developer or a CI runner wants to sign an artifact, they authenticate via OIDC. Fulcio checks this identity and issues a short-lived certificate bound to that specific email or workload. Because the certificate expires almost immediately, even if a key were intercepted, it would be useless by the time an attacker tried to use it. This keyless flow is a game changer for NPM maintainers who used to struggle with secure local storage of PGP keys. In the real world, this eliminates the risk of old, forgotten keys living in a former employee's laptop or a misconfigured environment variable. But wait, the certificate expires in 10 minutes. How can a user verify the signature months later? Payoff, this is where the immutable transparency log comes into play. Rekor is the piece of the puzzle that ensures accountability. It's an immutable, tamper-resistant transparency log. When you sign an artifact using the Sigstore flow, an entry is created in Rekor that includes the signature, the certificate, and a timestamp. Because this log is public and append-only, anyone can audit it. If a build server is compromised and starts signing malicious packages, the evidence is recorded permanently in Rekor. It can't be deleted or hidden. For us as engineers, this means we can verify that a signature was valid at the time the artifact was created, even if the certificate has since expired. This creates a high-integrity audit trail that's essential for detecting supply chain compromises early. In practice, this log serves as the source of truth for the entire ecosystem. But theory is one thing, actually using these tools in your terminal is surprisingly simple. Teaser, let's look at the actual commands you'll use to sign your first artifact. The tool that ties this all together for the developer is cosign. It's a CLI that handles the complexity of talking to fulcio and rekor. In a modern NPM workflow, you don't even need to manage local keys anymore. By running cosign sign with a keyless flag, the tool opens a browser for ODC login, generates the ephemeral keys in memory, signs your artifact whether it's a container image or a package blob, and uploads the proof to rekor. Verification is just as easy. Cosign verify checks the signature against the transparency log and ensures the identity matches what you expect. This is how we move from "I hope this package is safe" to "I know this package was signed by this specific CI job on GitHub." We've secured the who of the package. Payoff, however, knowing who signed it doesn't tell us what is inside, and that's why we need an SBOM. Think of an SBOM, or software bill of materials, as the nutritional label on the back of a food package. If you're allergic to peanuts, you check the label. In software, if a new vulnerability is announced in a deep dependency like globparent, you need to know instantly if you're using it. There are two main formats: SPDX, which is an ISO standard and often used for license compliance, and CycloneDX, which was built specifically for security and automation. In the NPM ecosystem, CycloneDX is rapidly becoming the winner because of its lightweight JSON structure and support for VEX, vulnerability exploitability exchange. VX allows maintainers to say, "I use this vulnerable library, but my code doesn't call the vulnerable function, so we are safe." This prevents unnecessary panic during security audits. If CycloneDX is the standard, how do we generate it without adding hours to our build time? The rule in modern engineering is simple. If it's manual, it's broken. You should never expect a developer to manually update an SBOM. Instead, we use tools like Sift or Trivy integrated directly into our CI/CD pipelines. For an NPM project, Sift can scan your package lock JSON and your node modules to generate a comprehensive CycloneDX JSON file in seconds. This file should then be attached to your release as an artifact. In GitHub Actions, you can automate this so that every pull request or release tag triggers an SBOM generation. By signing this SBOM with cosign, the tool we just discussed, you create a cryptographically verifiable record of exactly what went into that specific version of your software. Payoff, once you have this automated, you transition from reactive firefighting to proactive management. The true power of an SBOM is realized during a zero-day event. Remember the chaos when Log4j or Heartbleed hit? Most companies spent weeks just trying to find where they were vulnerable. If you have a centralized repository of SBOMs for all your microservices, that search takes seconds. You simply query your inventory for the vulnerable package name and version. An SBOM provides a living inventory that maps every component in your stack to known vulnerability databases. It moves security left by allowing you to catch issues before deployment, and right by allowing for instant impact analysis of new threats. We've now covered who signed the package and what is inside it. Teaser, but there's still one gap. How do we prove that the build process itself wasn't tampered with? That's where SLSA and provenance come in, which we'll tackle in the next chapter. Automation in your CI/CD pipeline is a double-edged sword. Most teams assume that because a build is automated, it is secure, but that is a dangerous fallacy. In the field, I have seen production environments compromised because an attacker injected a malicious script into a shared build runner that lacked environment isolation. This is the classic failure of SLSA Level 1 environments. To move to Level 2 and Level 3, we need more than just scripts. We need cryptographic signatures and hermetic builds where the network is restricted and the build environment is as ephemeral. Level 3 is the gold standard, ensuring that even if an attacker has access to your source code, they cannot easily manipulate the build process without leaving a digital footprint. We are shifting from trusting the process to verifying the paths. But even with an L3 build, how do you prove it actually happened where you said it did? Question: this leads us to the critical concept of the software birth certificate. Provenance is essentially the birth certificate of your software artifact. It is not just a simple log, it is a verifiable, cryptographically signed record of how, when, and where an artifact was built. In my experience, when a vulnerability is discovered, the first question isn't just what is the bug, but where did this binary actually come from? Without provenance, you are guessing. An attestation provides a statement about the artifact linked to a specific commit hash and a specific build workflow. By using Sigstore to sign these attestations, we create a tamper-proof link between the source code and the final npm package. This effectively kills the works on my machine excuse and replaces it with verified by the pipeline. Payoff: how do we automate this trust without passing around dangerous, long-lived API tokens? This is the death of the npm token secret. I have seen far too many security postmortems where a leaked CI secret led to a full supply chain takeover. Trusted publishing on npm uses OpenEd Connect, OADC, to eliminate this risk. Instead of storing a long-lived, high-privileged token in your GitHub secrets, the CI runner requests a short-lived token from npm by proving its identity through OADC. This means there is secret to steal, no secret to rotate, and no secret to leak. It is a fundamental shift in how we handle credentials in the cloud-native era. When your GitHub Actions workflow runs, it identifies as this specific repo and this specific workflow, and npm trusts it just for that session. Question: we've built a secure package, but how do we stop the production cluster from pulling a fake one? Verification must happen at the gate. If you are running Kubernetes, an admission controller like Kuberno or the Sigstore policy controller is your bouncer. It is not enough to just sign artifacts. You must enforce their validity before they enter your cluster. In modern DevSecOps, we define policies that say, only allow containers that have a valid SLSA attestation from our internal build organization. If a developer accidentally tries to deploy a container built on a local laptop, or if an attacker tries to swap an image for a malicious one, the admission controller blocks the pod creation instantly. This is where the trust but verify philosophy becomes automated enforcement. Payoff: doing this at scale requires the right tools. Let's look at how we verify these artifacts manually first. To see this in action on the command line, we use the SLSA verifier tool. It is the bridge between a raw binary and its security context. It is not enough to check a version number. You want to verify that the package was produced by a specific GitHub Actions workflow. In a real incident response, this tool is your best friend to confirm if a specific version of a dependency was actually built by the legitimate maintainer or a malicious actor. When you run this command, it checks the transparency logs and verifies the cryptographic signature against the OADC identity. If the output says verified successfully, you have a mathematical guarantee of the artifact's origin. Question: in the near future, we won't even be running these commands ourselves. What comes next? By 2026, we are moving toward agentic governance. Imagine AI agents that do not just scan for vulnerabilities, but actively monitor the entire graph of your supply chain's provenance in real time. They detect anomalies like a build taking 10 seconds longer than usual or a new dependency showing up without a SLSA L3 badge and automatically isolate the artifact. This is the final evolution of the shift-left movement. We are moving from static policies to dynamic, intelligent oversight. Security is no longer a checkbox, it is a living system. In the next chapter, I will take you into the trenches with real-world war stories where these defenses saved or could have saved major production environments. Teaser: next up, war stories and mitigation strategies. In the field, we don't just worry about theoretical exploits, we live through them. In late 2021, the NPM ecosystem was rocked by the hijacking of high-profile packages like WAParser, JSCO, and ERS. These aren't obscure libraries, they are used by millions. Attackers compromised maintainer accounts and published versions that contained credential stealers and crypto miners. Your Lockfile, which you thought was a shield, actually became a trap. It pinned you to a specific, malicious version that looked perfectly legitimate. I've seen teams spend entire weekends scrubbing production environments because a single automated CI job pulled a patch release that was actually a Trojan horse. These incidents prove that account-based trust is a single point of failure. When a maintainer's password is leaked, the entire chain of trust collapses instantly, and the resulting chaos in production can take days or weeks to fully remediate. This isn't just history, it's a recurring pattern of how supply chains are weaponized. When these incidents occur, the critical question is always, how quickly can we detect and contain the blast radius? Traditionally, we waited for a community member to notice a suspicious process and post a GitHub issue, but by then, thousands of servers were already infected. If we had integrated Sigstore logs back then, we would have seen an immediate anomaly. The identity signing the package wouldn't have matched the usual maintainer's OADC profile, or the build wouldn't have originated from the verified GitHub Actions pipeline. Real-world incident response in 2026 demands this level of transparency. Instead of reactive firefighting, we need proactive verification where any package without a valid SLSA provenance is automatically blocked from entering the production build stage. The lesson learned is clear: trust, but verify is no longer enough. We must verify before we ever trust. This shift from manual oversight to automated cryptographic verification is what separates a resilient infrastructure from a vulnerable one. In my experience, the safest way to handle the volatile NPM ecosystem is to implement a package quarantine. In a professional environment, you should never be the first person to install a version that was released 5 minutes ago. By introducing a mandatory 24 to 48-hour delay before allowing a new package version into your internal registry, you give the global security community time to identify and report any malicious activity. This strategy involves using a private proxy like Verdactio or Artifactory to curate your own blessed repository. Compare this to the direct access model, where every developer's machine is direct conduit for any code published to the public registry. One approach prioritizes raw speed, while the other prioritizes architectural integrity. In the field, we find that this delay rarely impacts feature delivery, but it has saved countless teams from being the patient zero of a new supply chain attack. It's about building a buffer between the chaotic public internet and your stable production environment. Finally, let's look at the actual checklist you should implement in your local development and CI/CD pipelines right now. First, set ignore scripts to true in your global configuration. This prevents post-install malware from executing during a simple install. Second, always use npm-c or pen-npm install frozen lockfile in CI to ensure that no unexpected dependency shifts occur during the build. We also need audit C to fail builds automatically if a vulnerability exceeds your risk threshold. In the field, I've seen developers get lazy and bypass these checks for just a quick test, which is exactly when accidents happen. This defense matrix isn't just a list of tools, it's a discipline. By hardening your local environment and enforcing strict audit rules, you turn your supply chain from a fragile link into a reinforced chain of trust. This is the baseline for any engineering team that takes security seriously in 2026. Now that we've covered the practical defense, let's look ahead to how the industry is evolving to make these manual steps even more robust. Look, I know this feels overwhelming. You've got a massive backlog of features, and now I'm telling you to overhaul your entire CI/CD pipeline. But in the real world, you don't do this all in one afternoon. For the first 10 days, your priority is trusted publishing. Stop using long-lived NPM tokens stored in your GitHub Actions secrets. They are a massive liability waiting to be leaked. Switch to OEDC-based publishing immediately. By day 20, you start generating and verifying SLSA provenance. This isn't just about showing a badge on a README, it's about programmatically ensuring that the code in the package actually came from your specific repository and not a malicious actor's machine. Finally, by day 30, you enforce these checks. If the provenance isn't valid or the SBOM reveals high-risk vulnerabilities, the build must fail. This phased approach moves you from hoping for the best to verifiable security. It's a journey from manual anxiety to automated trust. But how do we ensure this doesn't just become another forgotten checklist? I'll show you the philosophy that keeps these chains from breaking. After years in the trenches, I've realized that security isn't a product you buy or a single npm install away. It's a culture of continuous trust. In 2026, attackers won't just go after your production servers. They'll go after the very tools and dependencies you use to build them. If you treat security as a one-time setup, you've already lost the war. Every line of code, every third-party dependency, and every build script is a critical link in your supply chain. If one link is weak, be it a compromised maintainer account or a malicious build runner, the whole chain snaps. We have to move toward a world where unverified means unusable. By adopting Sigstore and SLSA, you aren't just protecting your own code, you're contributing to a healthier, safer ecosystem for everyone. This is the new standard of professional engineering. Remember, a lock file is just a snapshot, but a secure supply chain is a living, breathing promise to your users. This concludes our journey through the NPM supply chain. Now go out there and build something that stays secure.